Earth Science, Chapter 6, Section 6, Mineral Resources on Earth. Digging deeper. Mineral resources on Earth. Mineral resources in the ocean. Almost all of Earth's mineral resources are on the continents. The water of the oceans contains huge amounts of chemical elements. However, for the most part, the concentrations are extremely small. For most of these chemical elements, the cost of extraction makes it impractical to use them as mineral resources. Gold is a good example. Its concentration in ocean water is only 0.011 millionths of a gram per liter. That adds up to more than 10 billion total kilograms of gold in the oceans. It is far greater than the known reserves of gold in continental ore deposits. The technology used to extract gold from seawater is difficult and expensive. It is not at all economical. Great areas of the deep ocean floor are covered with dark-colored, rounded masses. Many of these areas are found in the Pacific Ocean. The masses are called iron manganese nodules. They range in size from golf balls to large fists. They consist of very fine-grained minerals of iron and manganese, with many other chemical elements in smaller concentrations. Techniques for mining them from the ocean floor have been developed. However, there are two problems. The sediment stirred up and suspended in the water during mining would have a harmful effect on the deep ocean environment. Also, the open oceans do not belong to any one country. They belong to humankind as a whole. Mineral resources of the continents. Earth's continents are geologically old. The oldest continental bedrock is 4 billion years old. This is only half a billion years younger than Earth itself. Also, large areas of Earth have bedrock that is older than a billion years. However, the geologic processes that form the bedrock record work on short geologic time scales. This means that there has been plenty of time for the geologic record of the continents to become very varied. Look at the geologic map of the United States shown in Figure 3. It shows a jumble of irregularly shaped areas. The areas are colored in with a variety of colors and patterns. These are rocks of different types and different ages. You can see that a large part of the United States has complex geology. Only a tiny fraction of the rocks of a continent are ores. Most rocks do not contain economically valuable minerals. These include rocks such as sandstone, shale, limestone, granite, basalt, schist, and gneiss. However, many are used as building stones. Also, limestone is used in making cement and glass. Ores are formed only in very specific conditions. Metal mining operations in the United States take up much less than 0.1% of the total land area. Look at the geologic map of the United States in Figure 3 above. Notice that large areas have only one or a few colors. These represent sedimentary rocks. In these areas, a blanket of sedimentary rocks covers the rocks deeper in Earth's crust. The rocks are layered nearly horizontally. In most places, these sedimentary rocks have never been buried very deeply. They have not been subjected to ore-forming processes. In contrast, Most areas of the western United States and some areas of the eastern United States show a complex pattern of rock types. There's the western United States, and here's the eastern United States. These areas are called orogenic belts. The word orogenic means mountain building. These are areas where collisions between Earth's lithospheric plates have resulted in a great uplift of the land surface. Mountains have been formed. In many places, these mountains have been worn down from their original heights. In some of those areas, igneous activity has led to deposition of various ores. One of the most important processes that forms ore is called hydrothermal activity. Magmas contain many valuable chemical elements. These elements are in very small amounts. They become concentrated in water-rich juices. These juices are left over after most of the magma has crystallized to form ordinary igneous rocks. These elements tend not to be included in the main minerals that crystallize from the magma. These juices work their way upward toward the surface. As they move upward, they cool. This causes a great variety of unusual minerals to crystallize. Many deposits are valuable ores. One example of this is a hydrothermal deposit. See figure 4 below. Much of the copper, zinc, tin, lead, mercury, gold, silver, platinum, and so on come from hydrothermal ore deposits. Ores of iron and aluminum are the two most used metals. Almost all iron ore comes from special sedimentary rocks. These rocks are very rich in iron minerals. These minerals were deposited in the oceans far back in geologic time. In the United States, these rocks are mined for iron ore. The mining takes place in northern Minnesota and northern Michigan. Aluminum ore consists of aluminum oxides. These are formed when rocks that contain aluminum are weathered at Earth's surface in warm and humid climates. Aluminum ore is also called bauxite. Some bauxite is mined in the United States, however, most comes from other countries. Mineral resources around the world. Some countries are richer in mineral deposits than others. Countries that have large areas of very old continental rocks are especially rich in mineral resources. Canada, Russia, Congo, South Africa, Brazil, and Australia are some examples. The United States has lots of energy reserves. These include coal and natural gas. However, it is not as rich in most mineral deposits as other large countries. The United States has abundant iron, copper, and tin deposits, yet almost all of the aluminum must be imported. This is also the case for ores of several special metals that are important in making steel. These include nickel, cobalt, and chromium. The United States government stockpiles important materials. Excuse me. The United States government stockpiles important metals. This is done in case supplies from other countries become reduced or cut off in the future. Finding minerals. Looking for mineral resources relies on many factors. Observation, data, and analysis is crucial. A good understanding of the geosciences is important. Experience is also valuable. However, there is still quite a lot of uncertainty. Minerals may not be in the places prospectors expect them to be. Also, even if a mineral deposit is found, problems can arise. There is no guarantee that it is concentrated. It may not be profitable to extract a mineral deposit if it is not highly concentrated. Exploration is very expensive. Drilling is the most expensive way to explore. However, it is the only sure way to confirm the type and amount of minerals present. In mineral exploration, drill holes are often at least 300 meters deep. They may cost $150 per meter. In oil exploration, a single drill hole may cost millions of dollars. Geologists try to avoid spending money on dry holes. They use other ways to find out more about what is below the surface. This helps them to eliminate areas with low exploration potential. Similar to oil production, mining projects often Similar to oil production, mining projects often depend on the market price of the mineral. For example, if the price of gold is high, then mining companies can operate even if production costs are high. They can still make a profit. However, if prices fall, then production of deposits with higher costs is often stopped until prices increase again. Mapping. Geologists map the surface by examining rock types in the field. They know that all mineral deposits are associated with specific kinds of rocks. Therefore, they can look for those specific rocks as guides to ore. They do this before any other kind of work. Then they look for folds, faults, and fractures in the rocks. They also look for any unusual colors and rock formations that do not seem consistent with the surroundings. They also may take rock samples to analyze in the laboratory. Then they record all the information on a map. Geologic maps, such as the one shown in Figure 5, help geologists infer what lies below the surface. Geochemistry. There is no guarantee that what is on the surface is also found below the ground. Geochemists study the chemistry of rocks and minerals. Samples taken at the surface from pits dug in the ground or from a few drilled holes can be analyzed. This can determine all the chemical elements present. These elements may be present in very small amounts. They can be just a few parts per million, ppm. They show up as halos above or around valuable mineral deposits. Along with sampling rocks and soil, geochemists may also sample vegetation and water. Elements from the deposit can be absorbed by plant roots or dissolved in water. Their presence can help geochemists determine whether a mineral deposit might be below the surface. However, a geochemist cannot tell how far below the surface the mineral is. Geophysics. The geophysicist is another important part of the exploration team. Oil and mineral companies employ thousands of geophysicists worldwide. Geophysics involves measuring properties of rocks and minerals. In oil exploration, the most common geophysical technique is a seismic wave reflection. A vibration is caused by a small explosion. It can also be created by striking the ground with a steel plate. The vibration travels through the crust. It is then reflected to the surface by a rock layer. The returning vibration is recorded on a special instrument. It is called a geophone. It records the time it takes for the vibrations to return to the surface. This tells the geophysicist about the depth to the reflecting layer. With this information, the geophysicist can more accurate, excuse me. With this information, the geophysicist can more accurately determine if the subsurface is folded or faulted. It can also reveal if there are other features where oil, gas, or mineral deposits may build up. Geophysicists also measure the local strength of, Geophysicists also measure the local strength of Earth's gravity field. This is affected by the density of the rocks below Earth's surface. Dense rocks cause a slightly greater gravitational attraction than the less dense rocks around them. As a result, gravity at the surface is slightly greater. Most ores are denser than the common rocks in Earth's crust. Granite, basalt, sandstone, and limestone are less dense than ores. The gravity field over most ore bodies is a bit stronger than over nearby areas. An instrument called a gravimeter measures the acceleration due to gravity. It can detect small differences in Earth's gravity field. You would weigh slightly more over an ore body than elsewhere. However, you could not feel it. Other techniques. An instrument called a magnum excuse me, an instrument called a magnetometer is used to detect changes in Earth's magnetic field. Rocks that contain a lot of iron-bearing minerals affect the local magnetic field. Geologists can also measure how well rocks conduct electricity. Geologists put electrical current in the ground for exploration. Most of the current flows through water in the pore spaces of rock. If a rock conducts electricity very well, it is likely to contain one of two things. It may just contain a lot of water. It also may contain a lot of metallic minerals. The bottom line: there is no exploration technique that can give a complete picture of what is below the surface. The geologist must be able to assess the data collected. It is important to look at all the clues to find minerals. Millions of dollars are spent on exploration. However, only a very small number of explored areas become profitable mines.